lot going on. If you wanted to tell someone about a galvanic cell, let's just say it's galvanic, that you had, that you were running, that you wanted to put together, communicating it through this drawing would take a really long time, and it's kind of a pain. So we do have a shorthand cell notation. And so I'm going to write this out, and then I'm going to define the pieces for you. So we could write that same galvanic cell by saying M solid, single vertical line, M plus aqueous, double vertical line, M prime solid, single vertical line, and M prime plus aqueous. Okay. So on the left, this is everything in the anode. So you always list the anode first. And everything on the right is the cathode. The double vertical line represents the salt bridge. And the single vertical line we use to indicate phase separation. So I'll kind of arrow from here. But remember, we do have it on both sides. Phase separation between the electrode and the solution. So these are the pieces that matter. The anode is on the left, the cathode is on the right, the single line separates phases, and the double line shows the salt bridge. Within the anode, it doesn't matter if you list the electrode first or second, right? Because you can see in the anode, I listed the electrode first. I also listed the electrode first in the cathode, but you will see some examples that maybe have, we'll say, same, no, we'll actually say equally correct. It would be equally correct to write M plus aqueous, single line, M solid, double line, and then we could go in either order on the other side as well. So let's just go ahead and flip those two. M prime plus aqueous, single line, M prime solid. So as long as I have anode on the left, cathode on the right, single and double lines in the right places, that's a totally fine way to write it. Okay, so identifying what's happening at each end, there is a bit of a mnemonic device to help you with this. So the anode is where oxidation happens. And you can remember this by, they both start with vowels, or to go along with that, some people remember anox to remember that they go together. So if oxidation is happening, then that means it's losing an electron. So M solid is turning into M plus aqueous plus an electron. The cathode is where reduction happens. They both start with consonants. So this means the M prime plus aqueous is gaining an electron to turn into M prime solid. And this should match with how we initially set up our picture of the cell. So overall, the reaction that I have happening, if I just add these two together to show my total reaction, it's really that M solid is reacting with M prime plus aqueous to turn into M plus aqueous and M prime solid. I don't see any of my electrons, even though they were transferred during this reaction, but this reaction is happening without the M solid actually touching the M prime plus. So it all happens through the wire, which I think is very cool. But I think all of this stuff is very cool. So that's, I guess, my personal problem. Okay. So I want to do 2 examples for kind of some more explicit cell notation. So what I'm going to do is pause the video here, get the reactions written out, and then we'll do a little practice. All right, so I have 2 examples that I want to look at. So the first one, we have zinc solid plus copper 2 plus aqueous turning into zinc 2 plus aqueous plus copper solid. So first, we can see that this is a redox reaction, which is something that we have looked at before. We haven't quite talked about how to balance them, unless you did look at this earlier. But what we need to do in order to get this into shorthand is identify what happens at the anode so that we can get that on the left-hand side of our cell notation, and then the cathode goes on the right-hand side. So we need to first pull out what is happening in the oxidation. So if oxidation is losing electrons, the thing in this reaction that's losing electrons is my zinc solid, because it is turning into zinc 2 plus, which it loses 2 electrons when that happens. So what's left over has to be the reduction, and we can check this. This looks correct. Copper 2 plus as an aqueous has to gain 2 electrons in order to turn into copper solid. So for my shorthand cell notation, this is the anode, this is the cathode. So I need to write my zinc information first. And again, it doesn't matter what order we do this in. I'm just going to kind of go left to right with my reaction. So solid zinc is my electrode. So I need a vertical line to separate it from the zinc 2 plus aqueous. Salt bridge. And then in copper, I have a copper 2 plus aqueous solution. And then phase separated from my copper solid electrode. So this is the shorthand notation that goes with this full reaction. Okay, my next one, this looks like a mess, right? This is a huge reaction. This is what a lot of redox reactions look like when they're fully balanced in solution. But we do have the ability to pull out of here what we need. So this would be a really good place to pause if you need practice with assigning oxidation numbers. Go through and see if you can assign the same things being oxidized and being reduced as we're going to get. Okay, so hopefully you paused to do a little practice. I'm just going to kind of underline some stuff. So I have iron 0 on this side. Let me find iron on the other side. And it has a 2 plus. So my iron was oxidized. So it's going to be at the anode. And the reaction that happens here, I've got 5 iron solid turning into 5 iron 2 plus aqueous plus 10 electrons. The 10 seems a bit high, but right, it's 2 for each iron, and I had 5 irons. You will sometimes not see these with the matching balancing. You might see the reduced coefficient form when people do this because it doesn't matter for indicating in the cell notation if we have the stoichiometry correct, but it matters very much when we have it in the full written reaction. So you'll see it either way. I'm going to stick with this reduced form just because it's a little bit easier to write. So for some of these longer reactions, I'm just going to underline everything else that's in here that we didn't include. And we've got some weird stuff like the H plus and the H2O, but that just seems to kind of balance it out. The real thing that I have going on is my MnO4 turning into Mn2 plus. So this is a redox reaction because that MnO4 has a manganese with a +7 oxidation state, so it has to gain electrons to get to the Mn2 plus. So that's the cathode because it's gaining electrons. It's reduction. So I'm just going to write out everything that's left over, which is, oops, I want that in black, 2 MnO4 minus aqueous plus 10 electrons plus 16H plus turning into 2Mn2 plus 8, that's aqueous, H2O liquid. Okay, that's a lot. The fully reduced form, we don't need to write all of these extra pieces. But you'll see when I put it into the full cell notation, I'm going to drop those coefficients and just list the actual components that are there. So when I start to do this, thankfully the anode is pretty straightforward. There's not a lot here. So when I put the anode on the left-hand side, I've got solid iron, single line because that is phase separated from the iron 2 plus aqueous. That's everything for the anode. So I'm going to put a double line for my salt bridge. On the right-hand side, I've got a lot of stuff that's aqueous. So it's all going to end up in the same section because if it's aqueous, it's in the same phase. So let's just start listing those and see where we're at. So the MnO4 minus is aqueous. And the H plus is aqueous. So I'm going to put a comma to separate these because this is the first time I've had multiple things that are aqueous. I do have aqueous H plus. I also have aqueous Mn2 plus. I don't have to list the water because it's accounted for in the fact that it's aqueous. And that's everything, but I don't have anything to put on the other side of my single line. So I did say it's required to have an electrode in order for your cell to run, but my reaction doesn't have any electrode listed here, so that's kind of an issue. However, it's not a problem. We can fill it in. So no electrode, no problem. If the reaction does not have anything that is a solid metal, you can add any metal that won't react just as some kind of surface to pick up electrons. So what we are going to do is add an inert metal electrode because this solid surface is required. You will see quite a few options for inert metal electrodes. Platinum solid and palladium solid are always the easiest. to write in here. Now, in practical terms, they're not the easiest to use because they are expensive metals. So you will also see in some places a graphite rod is used. So graphite is just carbon, but because of the way the carbon atoms are attached to each other, it can conduct electricity really easily. So when you do this, say in a lab, you'll probably use something like a graphite rod, but for the purpose of our shorthand cell notation, we can just throw in some platinum solid and our cell notation's complete.